I'm Sayoshi Nakamario, and this is a little deep dive into the Badgers.cash contracts. So this is the GitHub. It's under Sayoshi Nakamario Badgers Stake. And this just gives a quick overview of it. And the only real contract that is in it is this badgerstake.cash. This .opcodes version is the same contract, just with a different formatting. But first we'll go over the original one. So with this contract, the little formatting thing I have going on is that it shows the inputs and the outputs for the function that you're calling. So this is the lock function, which you can see right here. When you do the lock function, you have to give it an amount, a number of blocks you want to stake for, and the pub key hash that belongs to your address. And in this transaction, it has two inputs. 0 is a master badger. It is an NFT, and it is from the contract. So this is the UTXO that has all of the Badger tokens locked to it. And you're basically liberating some of them from this UTXO after you unlock. The next input is your BCH that you're locking up. And this is coming from you. And it shows BCH there because there's no tokens involved with that UTXO. For the outputs, after this transaction is built and submitted, it'll be recreating the master badger, which is input 0. It'll create a brand new lock UTXO, which goes to the contract, and it's an NFT. And this NFT is the same category as the master badger. So this input 0 is a minting NFT, which allows it to create its own child NFTs. And then optionally for output 2, you could have a change output of BCH. So if you send 10 BCH in input 1, but you only want to lock up 2 of it, then 8 BCH is allowed to go back to your address. So the parameters are for the function. So first we have an integer of an amount. So this is the amount of BCH in Satoshis that you want to lock up. We then have the integer blocks, how many blocks you want to lock up for, and one block being 10 minutes on average on BCH. And then the pub key hash, so this has to do with your address. So it's not literally your address, it's a pub key hash of it. So this is kind of where your address is derived from. So it might look a little different than what you're used to if you're expecting an address. But it's kind of interchangeable if you think about it in a simple way. So when you actually run the contract and it's verifying things, I have comments for every line here. So first one is that this active input index must be 0. So that means this contract, when you're pulling a UTXO from it, which in this case is this guy. So this master badger NFT is living on the contract, and this code is part of that contract. So if you want to interact with this UTXO, you have to call one of these functions to interact with that UTXO. So in this case, we're calling the lock function, and we're pulling the master badger UTXO from the contract. And we're saying that this UTXO must be position 0. It must be input 0. So that's what this line is doing. We are then checking the links and the inputs and outputs links. So we're saying that there must be exactly 2 UTXOs in this transaction, which you can see right here. There is 2. So if there's only 1 or if there's 3, it will fail and it won't allow it. The outputs has to be less than or equal to 3. So if we look, 1, 2, 3, less than, because you don't have to have the third input, or third output, sorry. You can only have 2, you can only have 1. The stake blocks, so the number that we're giving as the lockup right here, we put a condition on it that has to be less than or equal to 65,536. So that's the max value for a 2-byte number if we're restricting it. We then require that the amount that you're locking up has to be greater than or equal to 5,000 Satoshis. So you have to do at least 5,000. This gives the contract enough extra Satoshis to do an unlock later. So this is just something, once you calculate all this out and all these transactions, you need to have a few extra. So that's why I set it to that. Then the require, so we're checking. So in this case, we're looking at the transaction in total. So like this entire thing that we built, we're looking at input 0, master badger. we're checking its token category, and we're saying that it must equal this category. So this is the category right here, excluding the 0x. That's just saying that is hex. So that's the category of the master badger. And then we're also adding an O2 on the end of it, because that is the minting capability. So if you're just checking the category itself, that's going to be an immutable NFT, an NFT that can never change itself, its commitment. If it's an O1, that means it's immutable. That means the NFT can change its commitment, but that's it. And if it's an O2, that means it's a minting NFT. So it can change its commitment and it can create new child NFTs. So in this case, the master badger is a minting. So we're saying it must be the master badger's category and it must be a minting version of that one. And in this case, the only one that ever will exist is the master badger itself. So we've locked it down that we're using the correct NFT at that point. Then we also checked input 1. So input 1 is the UTXO with your BCH on it from your wallet. And we're saying that it must have no category. So it's a hex, but there's nothing after it. It's just empty. That means there's no cash token on that input. So you can't accidentally provide a cash token in the input. It is just raw, basic, normal BCH, and that's it. Next, we check the locking bytecode. So this version, okay, so you also give your pub key hash. So this is any pub key hash can go in here. Any random string of numbers or letters. There's nothing. No checks are done at this initial function point. But this is where it's used to actually do something. So we check input 1 and we get its locking bytecode. So we're looking at the user's bytecode from their transaction. So related to the input 1, we're looking at the bytecode and then we're saying that it has to equal a new locking bytecode for a pub key hash, paid a pub key hash, using the pub key hash that we're given. So this means you're giving the contract a pub key hash for some address. And at this point, it can be anything. However, that pub key hash, once we hash it and have a locking bytecode from it, that locking bytecode needs to equal what the bytecode is for the input 1. So that's saying whatever this pub key hash is, when it is hashed, it must equal what this input's locking bytecode is. So if you give it a fake pub key hash for somebody else's address, this will fail. This means that the pub key hash you're giving must be the one for input 1. And this is how it locks it down. So that even if you had a malicious website hosting, like creating, trying to interact with badgers, they can't do a lockup function call and give a bad pub key hash. It is always going to be the pub key hash that belongs to whoever is giving the BCH. Next, we look at the stake length. So in this case, I just had to convert the number or the stake blocks. So the stake blocks is given as an integer, a number of blocks that you want to lock for, say like 1,000. We then need to convert it into 2 bytes. So it's going from an integer into bytes. And we just call that stake length. And the reason we do that is because we then go into our output 1. So if we look under outputs, we're going to be creating the lock UTXO. So this is an NFT that is going to the Badger contract. So in this case, we are saying that output 1's commitment, this new lock UTXO commitment, is going to be comprised of the pub key hash that we gave. So this is representing your wallet. 18 empty bytes. So this is just a quirk that I did with it. So basically it's adding 18 zeros into the middle of it. And then we're adding the stake length. So you can't put an integer into a commitment. It has to be bytes, it has to be data, hex data. And that's the reason we convert right here. So we're just converting the integer number of stake blocks into bytes. And then we're putting your address and how long you're locking for into the commitment. And just because I added the 18 zeros there, this is inefficient. You could definitely do without this, but at the time I was learning and that's what I did. As an alternative, instead of providing an integer with stake blocks on your website side, you could do integers, but then just convert it into bytes before sending it to this contract if you made this bytes. So just when I created it, I made this an integer, and then I just dealt with the conversions. But a more efficient way would probably be to handle stake blocks as integers on your website and then convert it to bytes when you're building the transaction. And then this contract will just deal with bytes in the lock. And then you don't have to waste stuff right here or waste time doing this. Next, so in this case, we're finding the stake fee. So what we're doing is we're looking at input 0, going into its NFT commitment, and splitting the first 2 off of it. So what does that mean? So input 0 means the master badger. So the first 2 bytes of the master badger's commitment is the stake fee. So this is the 1,000 Satoshis is currently set to, but it can technically go up to 65,536. So all we're doing is pulling those first 2 bytes off of the master badger's commitment and saying and viewing what the stake fee is. So now we're looking at the recreating the master badger in output 0, which you see right here. So these rules are just verifying that that happens. So first we check the value, which is the number of Satoshis that the outputs can be created with. So we say that the value of it must be equal to the input value it had. So input 0, which is the master badger, and it must be equal to that plus the stake fee. So we get the stake fee from the input master badger, which is here, and then we add it onto the value it had. So if the stake fee is 1,000 Satoshis, which is what it currently is, then we're saying that the master badger must be original plus 1,000, and that's all that's doing. And then we're checking that the locking bytecode of output 0 is the same as the locking bytecode for input 0. And this is the line that's basically recreating the master badger at its current address and making sure that it goes back to the same address so that it keeps existing. Next, we check that the token category is the same. So again, so all of this is the master badger, which is why it's kind of grouped together. So this one is the token category. So we're recreating, so I guess if this is your first UTXO contract thing, I probably should have went over inputs and outputs for UTXO. You're actually destroying them on every transaction. So when you consume these 2 inputs, they are destroyed. And that is why on the outputs, we have to recreate the master badger. And for your BCH, some of the value will get sent into the lock UTXO, but we do have to recreate any change as well. So this original UTXO, you can basically think of as getting destroyed. So with this, we're defining the rules to verify that they do get recreated. So the token category, we're basically recreating this NFT. We're saying that the category that output 0 has must be equal to what input 0 had. And then for the NFT commitment, it's the same thing basically. All we're doing is kind of passing it forward. So we're saying that the input 0 NFT commitment must be the same as the output 0 NFT commitment. So we're basically just going from inputs to outputs, making sure it keeps living on. Next, we have stake reward. So this is how many badgers you're going to earn for your stake. So what it's doing is it's taking the amount. So this is the amount of Satoshis that you're going to lock up, and it's multiplying it by the number of blocks that you've locked up for. And then it's dividing it by this, which is just what, so this formula works out to being the 111 that Badgers uses. So basically you'll get 1 Badger coin for every 1 BCH locked up for 1 block. And if you have less than 1 BCH, then it multiplies on top of that. So if you have half a BCH locked up, it requires 2 blocks to lock up and actually earn 1 Badger coin. And so this is calculating how many Badger coins you get. We then do a check to make sure that your reward, the number of Badger coins you're going to get, is at least 1. It has to be 1 or higher. And if it's less than that, it won't work. The entire thing will just get rejected. So we've determined how many Badger coins you're going to get at a minimum amount, but they have to come from somewhere. So this is why the master badger exists. So the master badger has all of the badger coins that exist at Genesis. And the amount that it had was the maximum amount you're allowed to create on a cash token. And that amount, if we look at the cashtokens.org specification, is this number right here. So that's the maximum VM number, at least at time of the Badger contract creation. So that's how many the master badger was created with, and no more can be created. So that's it. That'll all that will ever exist. I don't remember the numbers off the top of my head, but if you want to get this many badger coins out of the master badger, it is going to take a long time and a lot of BCH. So the master badger has all those coins. It's slowly been giving them out. So because we've earned our stake reward, we have to deduct them from the master badger. So we're saying that the new master badger's output 0, so this is on its output, its token amount is equal to what it originally had minus whatever the stake reward is. Very simple. Calculate what your reward is in badger coins, make sure it's at least 1, and then deduct that from the master badger's input on its output. And then this one just has to do with the lock NFT that you're creating. So this is output 1. So if we look up here, output 1 is the lock UTXO going to the contract. So we're saying that the locking bytecode for it must be equal the same as the master badger. So locking bytecode, if you just think of it as the address, so the address of the contract or the address of whatever input you're referencing. So in this case, we're referencing input 0, which is the master badger. So this is just verifying it has to go back to the contract, or at least since this is brand new, it has to be sent to the contract. Also for the lock NFT, the token category is going to be the same as input 0, which is master badger. So its category, but we're splitting the first 32 bytes, and then we're adding a 1. So if you remember what I was talking about up here, this is the first 32 bytes. So this is the token category of the Badger contract. So we're saying take the Badger token category on input 0 and split the first 32 bytes. So you're just left with this. So basically that's just taking off the minting capability. So now we have an immutable NFT. But we're going to add an 01 to it, which is the mutable capability. So now we're creating an NFT that can change its commitment, at least in theory. Next, we are looking at the value. So we're going to create this lock NFT, its output value, and it must be the amount. So again, amount is the amount of Satoshis you're locking up. So this is just forcing that BCH to go on the lock NFT. And then the lock NFT's token amount is the stake reward. So the stake reward we calculated for the amount of badgers, it must go on this lock NFT. And then for the outputs, we are saying if the output's length is equal to 3, then the next input or output, which is output 2, must go back to output 1, and it must have a category of 0. So this is saying if your output 3, or the third output rather, so 1, 2, 3. So if you're the third output, if you exist, it must go back to input 1. Yes, input 1, which is this one. So if you exist, which in this case we know is change, it must go back to this. It must go back to the user's wallet that is interacting with this contract. And you must have no token category. Because if we remember, this guy right here, this master badger, is a minting NFT. That means you're allowed to create any number of NFTs in the transaction. So if we didn't have this output lock right here, so this is verifying that you can't have more than 3 outputs. 1, 2, 3. If you did not have this here, it was just deleted and there was no check on the output length. Because this guy, input 0 is a minting NFT, you could have an unlimited number of outputs up to whatever the 900 or whatever outer limit is, and they could all be NFTs. So that is why we're saying that we're putting a check in specifically that when we send BCH back to the user as change, it cannot have a token category. It can't be a Badger and it can't be minting. So this entire thing is just to verify that we can send change back, but it has to go back to the user that sent it in. It's a little restrictive because doing it this way, especially doing the number or limiting the number of inputs to 2, which we do right here, doing this causes the pain of having to have all of the BCH on one input. So if we didn't have that there, so if somebody had a 5 UTXO, a 4 UTXO, and a 3 UTXO, 543, you could combine all of those together and do a 10. But in this case, we don't allow more than 1 UTXO, so that person would have to first combine them into 1 UTXO that is 10 or higher so that they can do this function. And the downside of that is it's worse usability, UX for the user, but on the flip side, it does have a bit of a higher security because there's no way to potentially game where the change goes. There's gives and takes with this. It depends on the design. So pros and cons. It depends, more on what the overall system is going to be. I was very into locking it down as much as possible, but there's definitely use cases where you don't need to do that. So that is the lock function. We walk through the entire thing. All it's doing is verifying that the master badger gets recreated. It gives the reward for the badger coins and checks it and takes it off the master badger. It creates the lock NFT and verifies it has to go to the contract and that it is not a minting. And then in this case, sends change back to the user. Next would be the unlock transaction or function. So same thing, the inputs on this unlock. So when you actually unlock your Badger coins from the contract, all it has as an input is the lock UTXO that we created. So this is coming from the contract. After the transaction is finished, you basically have 3 outputs. You have the Badger coins, which I have as fungible token, I guess. It's been a while since I looked at that. So the Badger coins go back to you. A HoneyNFT goes back to you, and then again, change goes back to you. So unlock function has no parameters. Once again, this input active index must be 0. So saying that when you're pulling the lock NFT from this contract, it must be an input 0, sorry. And we are saying that there must be only one input in this entire transaction. So like it just enforces that that's the only thing that can exist. We are checking the outputs as well, saying that there can only be 3 and there must be 3. So actually this isn't optional. So to dig into this, so input 0, we check the token category. It must be a Badger category. It must be mutable. So this is true because we know when we just created the lock NFT, it had to have mutable on it as well. So that's all that's checking. It's making sure it is actually a lock NFT. Stake blocks. Actually, just to rewind for a second. So a note about this. I just remembered why it's immutable. The Badger coin contract is for the tokens. But this category is the category for the tokens, but it's also the exact same category for the Badger NFT series. So the 10,000 Badgers that are on the minting page of Badgers.cash. So those are immutable Badger NFTs. So they do not have a number on the end. The lock NFTs are mutable, so they have a 1 on the end, and I did that to differentiate them. So the lock NFTs, or the lock UTXO, is you can identify that it is locked UTXO because it is immutable. If it wasn't that mutable, this category would look the same as a Badger NFT. So this is just a way to differentiate them to make sure somebody didn't do some funny business for some reason to mint a Badger NFT off Badgers.cash and then send it to the Badgers contract and then be able to call this unlock, which I'm pretty sure I ran through it and it just doesn't work really, but just wanted to kind of cover that use case anyways. So next, stake blocks. So we're grabbing stake blocks from the lock UTXO, and we're splitting it at 38 bytes. So the commitments are 40 bytes max, at least currently. So we're going to split at 38, and we're taking the right side of that, which is what the 1 means. The 0 would mean we take the left side. So in this case, we're splitting it at 38, so we're taking the right, which is 2 bytes. And if we look up here to double check what the lock UTXO is saved as for its commitments, right here. So the lock UTXO gets created with the pub key hash, which is 20, 18 zeros, and then 2 for the stake length. So that is what we're taking off for the stake blocks right here. We're grabbing the stake length. And I called it stake blocks. Just, yeah, consistency. So we grab stake blocks. So this is the number of blocks you've locked for. We're doing the unlock function. So it's trying to check this. So it's saying that the transaction age, which is the number of blocks that this UTXO, this lock UTXO, must be at least this age. And an age, the age is the confirmations the blocks have had. So if you submit a lock UTXO on Badgers.cash and you let it sit there for an hour, on average, you'll have 6 confirmations. And that's what the age would be referring to. So if you did a lockup for 100 blocks, and that's what your stake blocks was 100, then it has to have 100 confirmations. So we're saying this must be true. We require that the current confirmations is greater than or equal to however many you set the stake blocks for. And this is an integer check, which is why we have to, a number check, so we have to convert the stake blocks, which is bytes. So we're pulling data from a commitment on an NFT, which is bytes. And so we have to convert it to integers, integer for this check. So this must be true. If this isn't true, the unlock will fail. Then we grab the payout address. So this is, so from the lock NFT, we're grabbing the pub key hash. So again, if we just scroll up here, just to be thorough, we're saying we're creating the lock UTXO with these 3 things right here. So we are now grabbing this pub key hash from it again. So if we come back down to the unlock function, we are saying the payout address is equal to that. So again, we're splitting at 20 and we're taking the left side, which is 0. So we've got the payout address now, that user's pub key hash. So now we have to do a hash on that pub key hash to get the address. So we're saying it's a new locking bytecode, pay to pub key hash, because this is just a normal user address. And we're giving it that pub key hash, and that gives us the payout bytecode. So this is, you could think of it as like the address that it has to go to. So we now know what the address of the user is. So now we are doing output 0. So as you see, all these are output zeros. So we are saying that the locking bytecode for output 0, which again is Badger coins, must be going to that payout bytecode that we just hashed. So it must go to the user's address. We're saying the token category must be equal to the Badgers category. So again, 32 bytes of it right there. And this is coming from input 0, which is the lock UTXO, which is a Badger category. And it must have 1,000 Satoshis on this Badger coin. And this is because this it needs Satoshis to exist. So you can't just have a token with no Satoshis on it, because the BitcoinCash network won't allow it to happen. It needs the minimum amount for it to continue existing, a dust amount. So in this case, we're just saying it needs 1,000 Satoshis. We then specify the token amount, and this is how many Badger coins it is. So the lock UTXO was created with the reward Badger coins that you were given. So that's how many it has on it in input 0, and we're saying that those Badger coins must be on output 0 as well. So they're just being transported from this lock UTXO to the Badger coin UTXO, which is going to the user. So we then focus on output 1. So this is a HoneyNFT. So again, we're saying that the output 1 locking bytecode must be going to the payout bytecode, which is the user's address. The output 1 token category is also a Honey Badger or a Badger category. So again, same category because we're referencing input 0. However, in this case, we're splitting the 32 bytes, which is the category, but there is nothing after it. So in this case, there's no mutable, there's no minting. That means this is an immutable NFT. So this thing's commitment, which we define in a few lines below, can never change. And then again, we give it 1,000 Satoshis on its value just so it can exist. And then we define the commitment. So we make a variable called commitments. We put 4 zeros on the front of it. So again, 0x saying that it's hex, and then 4 zeros is an actual value. And then we also put the token amount. So input 0, which is the lock UTXO, and we're referencing its token amount. So this is the number of Badger coins that the lock UTXO had, which is how many Badger coins you got for doing this lockup. And it's an integer, so we need to convert it to bytes because it is going to be going back inside a commitment. And then we specify that the commitment of output 1, which is, again, the HoneyNFT, must equal the commitment we just constructed. So this means that you are getting a HoneyNFT, and it has 4 bytes of 0 on the front of it, and then it has how many Badger coins you had for this lockup. So this does nothing currently. This does happen, and everybody has these, and they could be used for something in the future. I've had some random ideas floating around, and other people have had some other ideas floating around for their things. And this is just something to track over time how many coins you earned. In other words, how much BCH you locked up and how long for. Because the Badger coins themselves you might use for something, such as burning to mint an NFT, so you lose those. But this still gives you a reference of how many you did have in the past, which again, we can use for something maybe. And then output 2. So output 2 again is change. We're saying that again, output 2 must go to the payout bytecode, which is also the user's address again. The token category must be nothing. And the value of output 2, which is the BCH, must be equal to what is on input 0, which is the lock UTXO. So this lock UTXO is the BCH that you locked up. So we're saying that it must send it all back to the user's bytecode minus 3,000 Satoshis. And this is minus 1,000 Satoshis for the miner fee to cover this thing being called. It is also a minus 1,000 Satoshis right here for the HoneyNFT, and it is minus 1,000 Satoshis for the Badger coins on their UTXO. So these two, the user gets back. The Badger coin and the HoneyNFT, technically they go back to the user, so they don't actually lose it, but they do lose 1,000 because of the miner fee. And this is the reason why you can call unlock without needing to do a BCH transaction or provide an input with BCH yourself. If you go to the Badger's website, when you look at these UTXOs, all these lockup times, if there was one there that said unlock, you could click on it, and you don't need to have a wallet connected to the website. You don't need to have BCH. You don't need to know what BCH is because of the way this unlock function is set up and the fact it takes the BCH from the existing UTXO. So that's kind of the magic behind that. Next and last function would be the withdraw function. So this is something that you won't interact with using the contract. This is how I set it up for myself. So I have the fee, the 1,000 Satoshis for doing the unlock on the Badgers. I wanted a way to change it in case I needed to increase it, in case somebody tried to like spam the contract constantly and like kick out other people's unlocks and stuff like that. So this was a way for me to increase that fee in case stuff like that started happening, or if there's other bad congestion on it somehow. So what the withdraw function does, again, so we have 2 inputs, the master badger and a admin UTXO. So master badger, the same, you're calling it from this contract. The admin UTXO is just a normal BCH input. It doesn't have any tokens on it, but it is from admin, which just means it's from a special address that I control. The outputs, again, we're going to recreate the master badger. It also still has all like the badger coins that haven't been claimed, so obviously we need to recreate it. And it's going to send a withdraw UTXO, which is also just BCH, to the admin address. So the parameters for this, we need a fee. So a new fee. So this sets the master badger's locking fee. So again, it's the 0 to 65,000 number I mentioned. So this is this lockup fee right here. So when you're doing a lock function and you're putting BCH into the contract, we extract the lock fee or the stake fee in this case, and use that in the calculations for how much the master badger should get. So this is currently set to 1,000 Satoshis, and that is set on the master badger, and that is what this is interacting with down here. So to call this function again, you need to provide a new number for the new fee. So is it going to be 1,000? Is it going to be 2,000? Is it going to be whatever? So going through the contract, this active input index must be 0. So again, we're just saying the master badger must be in the first inputs. There can only be 2 inputs. There can only be 2 outputs, or rather there has to be. Once again, we're checking input 0's token category must be a badger category. Oh, and it must be a minting category. In other words, this must be the master badger because there is only one. We are then checking that input 1 has a token category of 0. So we're saying that the admin UTXO in input 1 must be BCH only. It cannot have an NFT or tokens on it. And in theory, I'm the only one calling this, so this is really just covering me, I guess. We're then extracting the admin address. So we are looking in input 0, which is the master badger, and we're splitting it at 20 and taking the right side. So the master badger, it has a commitment where the pub key hash is stored in it of the address that I control. So this is almost exactly the same as a lock NFT, where we're storing the pub key hash of the user's address inside of the commitment. This is the master badger has its own, and that one is just a random address that I have. So we then take that admin address, we once again hash it to pay to pub key hash, so we have the payout bytecode. So this is saying the admin address should be this address. And then we check, is input 1's locking bytecode equal to what we just determined? So this is the part that locks it down so that only that one address is allowed to interact with this withdraw function. So somebody else can call withdraw and somebody else can try to do this, but if they're using the wrong address, it won't work. We then check that output 1. So this is basically just all confirming the outputs at this point. So output 1's token category, again, output 1 is the withdraw UTXO to the admin address, cannot have a category. So this is saying basically that you cannot create new tokens such as another minting token. Only the master badger can be that to make the system work. Next is the value. So the output 1 value, which is the withdraw UTXO, it must be equal to the value of input 0. So that is master badger. The master badger has a Satoshi value that is very, very slowly going up over time. So as people do locks, 1,000 Satoshis get added onto the master badger for each lock. So it must be equal to whatever that total amount is the master badger has, and it must also have whatever the input 1 is. So in this case, the admin UTXO. So if I had, 0.5 BCH on this UTXO, that's what I was using. The output 1 must be equal to 0.5 BCH, which is what I originally had, as well as whatever the master badger had. But we're minusing 2,000 from this. So we're saying the master badger value plus my value minus 1,000 for the miner fee, and also 1,000 for the master badger. So it's kind of implicitly 1,000 is left for the master badger to keep existing. And which is right here, if we fast forward a little bit. So output 0's value must be 1,000. So this verifies at least 1,000, or exactly 1,000 rather, must remain on the master badger. And that's just so it keeps existing. So continuing, output 0, so this is the master badger. So we're saying that output 0's locking bytecode must equal input 1 0 locking bytecode. So we're basically saying that, this output must be going to the same contract as this. So just master badger recreating itself. Again, token category, same thing. Master Badger must have the same category. Again, has to be at least 1,000 dust Satoshis on it. Its token amount must be the same as it had before. So it has that gigantic number that it started with. So it's still going to have a gigantic number of Badger coins on it. Whatever it currently has, it must be sent back to the same UTXO on the output. And then the only other change is the commitment on the Master Badger. So if we look at input 0, so first we're getting the rest of the commitment. That's not going to change. So we're creating a variable called rest commitment. We're looking at input 0, which is the Master Badger. We're looking at its commitment. We're splitting it at the second byte, and we're taking the right side. So we're taking basically all of the commitment of the Master Badger except for the first 2 bytes. And then we're saying that the new Master Badger in the output 0, its commitment, must equal the new fee. So if we go all the way back up here, there is now a new fee that we're giving it. And again, it's an integer and we have to convert it to bytes. So we're putting the new fee at the beginning of the commitments, and then we're adding the rest of the commitment we haven't touched, which I believe is just the pub key hash of the admin address. And that's it. That is the whole withdraw function. That is also the whole Badger contract. So if you were able to get through this and follow it, that is the entire contract. That is how it works. And that's it.